Alright, today, non-renewable energy resources. So, non-renewable, can't get it back. Once it's used up, it's gone. Okay. Some of the most common forms, you have petroleum, coal, natural gas. There are differences between them. Collectively, they fall under fossil fuels, but they are not all identical. They're used for different things, they form different ways, all that good stuff. Petroleum. Most petroleum, what you consider oil, forms from marine life. These are dead plankton and critters and stuff in the ocean. They die, they settle to the bottom. Eventually, they get covered, they get squeezed, turned into petroleum, oil. Petroleum is also most commonly used for transportation purposes. It's the most commonly used fuel for transportation in the world. Coal, on the other hand, tends to be solid, and it forms from the remains of woody plants. Now, woody means it has some sort of stem to it. Not necessarily grass. It decomposes way too quickly. And natural gas tends to form where other fossil fuels form. Natural gas are hydrocarbons. The most common natural gas is methane, CH4. Okay. Now, fossil fuels only form under very specific conditions. They have to have areas that have water. It has to be stagnant, which means it doesn't move, and hypoxic, which is low or no oxygen. The three most common locations for fossil fuels to form: swamps, deep lakes, or deep ocean. And because they take millions of years to form, they're non-renewable. Pretty easy. Now, the most abundant fossil fuel worldwide is coal. Abundant, common. And coal is most commonly used to generate electricity. So, petroleum is used for transportation. Coal is used for generating electricity. Now, here's a little graphic showing the formation of coal. Here you have a bunch of dead plants. Over time, as they start to decompose, but they're still mostly vegetation, that's called peat, P-E-A-T. As you add pressure and heat, as you squeeze it, it gets hotter. It forms into lignite, which is the first stage of coal. It's the lowest quality coal. That's what this is for, but we'll get to that in a moment. Now, here you have these little droplets being squeezed out. That is generally water and methane. As you're squeezing that dead decaying matter, you're squeezing out the water. It gets squishy. So you squeeze that out. That's the biggest difference between peat and lignite, is the absence of moisture. Now here, we had sub-bituminous coal, but we don't care about bituminous, so I covered it up. Then we have bituminous coal. That's the next step of coal. After that is anthracite. Anthracite is considered the highest quality coal. Now we're going to get to those little pictures. Sulfur content. Sulfur content. Sulfur oxides are a greenhouse gas. They're an air pollutant. They don't want them. So here I have the word sulfur written. It represents the sulfur content of this type of coal. So sulfur is written really big. And then for bituminous, it's written kind of in the middle. And then for anthracite, it's written really small. Now, in the English world, they call that symbolism. This sulfur is written the biggest because it has the highest sulfur content. This one's written the little baby one because it has the lowest sulfur content. And then here we have some nice flames. We have a little flame, and then at anthracite we have a nice big flame. Lignite has the lowest burning temperature of all the types of coal, whereas anthracite has the highest burning temperature. So lignite will boil water much slower and less effectively than anthracite. The low sulfur content and other contaminants like mercury, and combined with the high burning temperature, are why anthracite is considered the highest quality coal. Thus, it's the most expensive, but it's the kind that if you're going to use coal, it's the least bad kind. And then there we go. Anthracite is the highest quality. The most common use of coal is for electricity generation. So in an ideal world, anthracite would be used for generating that electrical power. But, world's not ideal. Now down here, oops, we have a little star. Like most things in the world, they're not distributed equally and they're not used equally. The developed world, places like the US, Western Europe, etc., they use a lot more fossil fuels than the developing world. So they're not used equally. They're also used for different purposes. In places like the US, most fossil fuels are used for things like transportation, whereas in the developing world, most fossil fuel use is for things like cooking or heating your home. And then in terms of distribution, the US has more coal than any other place in the world, whereas areas like Africa have very little naturally occurring coal, so not distributed equally. And then, going back to petroleum, oh, whoops, I deleted that. It would help if I could spell. Not all petroleum is equal. When you pull it out of the ground, it's not just gas. It's not just engine oil. You have to refine it. You have to separate it. So what ends up happening there is you use this process called fractional distillation, where you separate those fuels based on their boiling point. The lower the boiling point, the simpler the molecule, and you can use it for more of that high quality stuff. So the lowest molecular weight, the lowest boiling point is methane. Methane, CH4. It's the simplest hydrocarbon molecule you can have. And then as you increase these boiling points, you kind of have lower quality, so you use them for things that don't necessarily require the highest quality. And then when you get down to the bottom, that leftover sludgy stuff, that's what you use for the lowest quality stuff. So asphalt, you drive around on it, it doesn't really need to do much. Now, petroleum is found everywhere. These are just some of the products that are made from petroleum. Anything made of plastic, a lot of things made of rubber. Lots of products you use every day are made from petroleum. There's a list. You don't need to know everything, but know some key indicator ones. Now, you've seen and heard this little statistic before that petroleum is running out. 1/2 of all the known petroleum has been extracted. That means it's been located and pulled out of the ground. Now, it says known petroleum. There could be more, we just don't know about it. Scientists and geologists are finding more, not all the time, but pretty frequently. So this estimate of all the fossil fuels are used up is fallacious. Until all of it has been discovered, you can't say how much of it has been extracted, but about half is the estimate. There's still more out there, but it is kind of running out. Now, in addition to those 3 big types of fossil fuels, we have some little ones, some other ways of getting fuel. We have fracking, hydraulic fracturing. That's found in areas with lots of shale rock. You have tar sands and synth fuels. Those are lower quality. Tar sands are also generally too expensive to be economically worth it to extract the petroleum, but in times of desperation, it's an option. And synth fuels are artificially created fossil fuels. Now, this diverse use of fossil fuels, of petroleum, has had some impacts. So, in the 1973, OPEC, the oil producing and exporting countries, put an embargo on exporting oil from mostly the Middle East. This led to gas crises in the US where people were lining up and fighting each other at gas stations for buying gas. It brought to the national attention that the US was really, really depending on these other nations for their oil to live their way of life. So to kind of increase that stability, to decrease that reliance on other countries, so if they ever tried something like this again, the US wouldn't be impacted as much, legislation was enacted that developed the Strategic Petroleum Reserve. It's about 700 million barrels, with another 300,000 being added every week, which seems like a lot, but at current rate of use, that's only about 1 month worth of oil. But if there ever is another embargo, using just that reserve, the U.S. can run for about a month. And this reserve is located in Louisiana. They store it underground in a bunch of caves, which is pretty neat. Okay, so those are fossil fuels. Now, popping over to nuclear energy. First developed in the 50s for commercial purposes. It was used for weapons in the 40s with Nagasaki and Hiroshima. You guys learned about that in history. Nuclear energy is responsible for about 20% of the electricity generation in the US. That number is about 75% in France, which is interesting because once you build the nuclear power plant, they're pretty cheap to keep going. So France makes about 3 billion euros per year exporting their extra energy. It's cheap enough that they can build it, generate it, and sell it to other companies for a profit, which I think is pretty cool. Now, here you have a picture of those iconic towers that you've all seen. Everybody knows that these little towers, those are nuclear power plants. Common misconception is that this stuff right here is smoke. Really, it's just water. It's steam. That's it. Nothing else to it. Just steam. Now, on this side, there are two types of reactions that are used to generate nuclear power. There's fusion and fission. Fusion is where you take two smaller molecules and you smush them together. You get one larger one, and then generally neutrons and energy as your output. Now, here's a little sad face, because fusion energy currently requires an input of energy. It takes more energy to put into the system to squeeze those molecules to get that release of energy than you get out of it. So it's kind of like spending $10 to make $5. It's not effective. The kind that is used on Earth by humans is fission, where you take a small neutron and you shoot it at a large molecule. Well, a large atom, my bad. And it splits. It turns into more neutrons, which I like to think of as more ammo for hitting other large atoms that split them apart and make more of these little bullets that hit more atoms and keep the process going. If you've ever heard the term chain reaction, that's what's going on here, because you have a neutron that hits a big atom, which releases neutrons, which then you can imagine this going back to here. This neutron is now hitting another big atom, which releases more neutrons, which hit more big atoms. It just keeps going. Chain reaction. So, stars like the sun use fusion and fission. Humans, fission is our way. Now, nuclear power plants generally use two types of fuel. There's uranium or plutonium. Now, just like fossil fuels, uranium has to be mined from underground. You have to get to it. It doesn't just appear. And that uranium is left over from the formation of the Earth. When the Earth formed, it had some radioactive isotopes. That's the uranium. It has a very long half-life, so the stuff from when the Earth formed is still here. But the world is not making more uranium, so it is a non-renewable resource, like fossil fuels, except it takes even longer to form. Now, most uranium that exists in the Earth is uranium-238. That means it's uranium with an atomic mass of 238. It has to be enriched to be used in nuclear reactors because uranium-238 doesn't output enough energy to keep that reaction going. It can't start and maintain its own chain reaction. So it has to be enriched into uranium-235, which, because it's less stable, it does emit enough energy to keep itself going. Now, as you use it, that uranium is decaying. As it's decaying, it's releasing heat. Here we go. As it decays, it releases heat. Heat is energy. Now, this heat is used to generate electricity the same way almost any other method is used to generate electricity. It heats water. That water turns into steam, which spins a turbine, which is connected to a generator, which generates that electricity through kinetic motion, which is sent out and used. But nuclear reactors have two different ways of using that water. There's a boiling water reactor, also called an open system, where if you look, you have water coming into the system. The water comes in. It's exposed directly to these control rods. Those control rods are the uranium. It's what's giving off the heat. That exposed water gets hot, turns into steam. That steam flows through the pipe to the turbine. That moving steam spins the turbine, which helps the generator generate that electricity. Then that steam gets sent to a condenser, where it's condensed back into a liquid, where it keeps going. The other way is a pressurized water reactor. Now, it functions kind of the same way, but rather than water being directly exposed to the control rods, you have water that comes in and it's heated and turned into steam, but it doesn't turn into steam from direct exposure to the control rods. You have a separate system, that's right here, of water that's exposed to the control rods. That water gets hot, and then through conduction, through this water touching this pressurized system, that's what makes it hot. That's what turns it into steam. And then that steam spins the turbine connected to the generator to make that electricity. That water that has never contacted the control rods then gets turned back into water and the system keeps going. The biggest difference between the two is whether the water is directly contacting the control rods or not. Okay. Now, the rate of decay is called the half-life of an atom. Now, these can be very, very long periods of time. For instance, the half-life of uranium is 700 million years. The half-life of plutonium is 24,000 years, which is much less, but still a really long time. Now, half-life is the amount of time it takes for half of a sample to decay. And then a common misconception, half-life is a rate. So it's not necessarily if it takes 10 years for half of a sample to decay, then in another 10 years, all of it has decayed. It's a rate. So that's what this little graph is for. Here, we have a made-up amount. If we start at 0.1, in 100 seconds, 1/2 of it has decayed. Now, in 100 seconds, half of it decayed, which means the half-life is 100 seconds. So in another 100 seconds, 200 seconds, another half has decayed. So if we started at 0.1, half of that is 0.05, my bad. Half of that is 0.025. So at the next half-life, 300 seconds, we have half of that remaining. If we put some absolute numbers on there, let's use 2,000. Let's say we have 2,000 pounds of radioactive material. After one half-life, we'll have 1,000 pounds. 2 half-lives, we'll have 500 pounds. 3 half-lives, we'll have 250 pounds. And then 125 pounds. You just keep dividing by 2 each time. You will almost guaranteed have a multiple choice question about this concept. in 2021 when your test has multiple choice questions again. Now, a byproduct of that decay of uranium is plutonium. Now, plutonium is considered a problem because uranium is generally not used in nuclear warheads. Plutonium is. So the more uranium you're using in your nuclear reactors, the more plutonium is being generated, which creates a risk of it being used to develop nuclear weapons. Also, because this half-life is so long, something needs to be done with it. It needs to be stored. Storage is a problem. Now, Yucca Mountain was an idea put forth in the 80s that you could take Yucca Mountain, excavate underneath it, and use it for extremely long-term storage of this highly radioactive waste. A lot of work has been done on this, but it's never been formally approved, so this is still just a pipe dream at this point. What is done with waste is that it's stored on site. You have the fuel, as it's used up and turned into waste, it gets stored either underground in concrete tanks or above ground in containment tanks where it has to stay. Now, it builds up over time, and because it's still radioactive and dangerous, it becomes more expensive and takes up more space to manage it. That risk of accidents and whatnot, developing nuclear weapons with it, increases. Yeah. Okay, almost done. Now, some benefits of nuclear power. Benefits, good things. It's safer for workers. Now, whenever you see movies and stuff, oh no, the nuclear reactor's melting down, we're going to get cancer, things like that. That does not happen often. It has happened 3 times in history at any sort of significant level. We'll talk about those in a minute. But in general, it's much safer for workers. Also, because the risk of nuclear reactors is higher, if something goes wrong, there are much stricter safety regulations put in place, which keep the workers safer. The only atmospheric waste is water vapor, which already exists, and human contributions to the water cycle are negligible. It also requires less mining. Okay, some negatives. There's the risk of it being used for weapons. It generates that radioactive waste. And then here we have accidents with a nice little yellow star. That's where we get to those 3 accidents that we've talked about. You do need to know background information about these. They could come up in FRQs, and they sometimes come up in multiple choice questions when you have multiple choice questions. There are 3 that you need to know. Make sure you know those. The first one is 3 Mile Island. The second one is Chernobyl. The third one is Fukushima. Now, 3 Mile Island was in the United States. It was in Pennsylvania. It happened in 1979. It was a result of mechanical failure compounded by human mistakes that were then further amplified by a pretty terribly designed computer interface, which then led to more human mistakes, but undummies, because in that case it wasn't human accident, it was mistakes made because of this terrible interface. One really bad example is that one of the warning lights saying, hey, there's a problem, was hidden. It was covered by something else. So even though it was going off saying there's a problem, no one could see it. Whoops. It resulted in a partial meltdown, and it released a bunch of radioactive iodine into the surrounding area. It's been almost 40 years since this happened, so the long-term studies that have been done concluded that there was a statistically insignificant increase in rates of cancer in the area. So overall, it didn't have a super long-term negative impact. But it was kind of the catalyst for increasing awareness of anti-nuclear movements in the U.S. This is when the dirty hippies finally gained some traction and got the public on their side that nuclear reactors were bad. And it was also kind of the death knell of the industry. The production of new power plants had already slowed for a few years before this, but after 3 Mile Island, about half of the planned reactors were just canceled, or if they were under construction, just left unfinished. So it wasn't responsible for the decline of the industry, but it definitely halted the growth of the industry. Yeah. 3 Mile Island. Chernobyl happened in the Ukraine, 1986. This is probably the most famous example. We're going to greatly oversimplify what happened. I highly recommend reading some more about it. It's super fascinating, even though terrible. I'm going to go over what happened, but again, this is very simplified. Basically, the Soviet Union wanted to run a test on the emergency systems of the Ukraine power plant, and they didn't prepare very well. They initially had it scheduled during the day, and they trained the day shift operators what to do, but an unexpected power outage in a nearby area required a delay in the test, so they ended up doing the test in the middle of the night during a shift change. So all the specialists they had on hand, all the people who had been specifically trained to be on standby during this test, were at home sleeping. They were also hoping, like, the point of the test was to see what the backup generators would do, because if they were off for more than a certain amount of time, the plant wouldn't get enough coolant, which would then increase the reactor temperature, which could lead to these self-sustaining reactions. The test failed. Instead of being off for approximately 1 minute, like it was supposed to be, they went off for about 10 hours instead. It was no good. And then the attempted solutions to the problem made the initial problems even worse. Again, this is an oversimplification, but basically the backup generators went down, the temperature increased, and the output of the power plant went way down. When power finally went back up, they tried to flood the control rods, which then generated a lot more steam, which current estimates are that it went about 3,000 times higher than it was supposed to in terms of output, which then caused big boom. There were actually 2 explosions, one that destroyed the containment field and then one that released the radioactive material. Again, super fascinating. It's an excellent study in cost cutting, being unprepared, not having properly trained people that try a solution that works short term but makes the entire problem worse. It's very interesting. And then the third thing is Fukushima. It happened in Japan in 2011. Unlike the other 2, this one didn't really have a lot of human error. It was just accident of nature that happened. The timing of it was bad. There was an earthquake that triggered a tsunami that made a wave. Then we're going to stop the cause and effect and pop over to here to talk about what happened next. After the earthquake, a bunch of the safety mechanisms in the plant worked. They did what they were supposed to. They shut down the main reactors. Everything was good. But the local power supply failed. So the backup generators in the power plant to keep things running kicked on. Now we're going to go back to this wave. When that wave hit the shore, it flooded the basement where the generators were stored. Flooded generators don't work, so those generators failed. Now, even though those safety measures had been enacted that reduced the output of the plant, you can't shut them completely off. With those generators failing, it caused 3 catastrophic failures in their reactors. They had essentially 3 Chernobyls at once. It was very sad. Okay, this was pretty long. It wasn't a quick discussion, but it covers the info you need to know about non-renewable energy resources. Yeah! I'm going to post the PDF of these notes in Classroom for you.